Hello, and welcome to the Building IQ 10 on the 10th Tech Podcast Series, where a range of artificial intelligence, machine learning, and data science topics are explored in 10-minute episodes each 10th of the month. To kick off our podcast series, today we have the pleasure of talking with Building IQ's Head of Products and Marketing, Steve Nguyen, about the future of AI-driven inference engines. Steve brings decades of tech experience to Building IQ and spearheaded the recent launch of the company's Epiphany inference engine. Let's explore what exactly AI engines are and why they are the future of intelligent buildings and beyond. Steve, thank you for joining today.
Thanks, Christine. Thanks for having me.
Well, let's kick off by laying down some basics. Tell us, what is an AI inference engine and why should we care about them?
Well, I think I'll tell you from our perspective, really the inference engine is all about understanding a data system with imperfect data. So that doesn't necessarily mean we don't have a lot of data. It just means that we may not have all of the necessary pieces to come to a conclusion about a system. So an inference engine helps us fill in those gaps, helps us identify relationships that we may not be obvious or in the design of the system, and kind of figure out what's going on inside of a data system without actually having all of, say, very detailed documentation.
Interesting. And so what sort of applications are AI inference engines used in today?
Well, they really span the gamut from consumer to industrial. At the moment, in the buildings industry, we don't really see any use of inference engines. We really see use of AI in general. And really, we're talking about machine learning specifically. For instance, BuildingIQ itself uses machine learning fairly extensively in our modeling and predictive algorithms. But as far as an inference engine is concerned, I believe we are at the forefront of that movement.
Well, tell us how those are different then.
Well, in the one sense, we're looking for just data pattern changes, data pattern matching, sudden changes in data. That's the way we're using machine learning, and then we train our algorithms to identify what's normal versus abnormal in these pattern recognition algorithms in general. That's simplified, but basically what's happening. With the inference engine, we're throwing out all of our prior knowledge and starting really looking at the relationships amongst data, either at the device level or even at the data point level, comparing both to each other and amongst each other, as well as to, say, a keystone point. In our case, we would be looking, for instance, at the whole building energy consumption as a key data point and grading all of the data points and how they move in relation in contribution to that whole energy metric. So it's really, if you will, context insensitive as opposed to context sensitive. And we're looking again at the relationship amongst data as opposed to a specific change in data.
Help us understand how this type of relational knowledge, which might have previously only been understood by an on-site facilities team, can be a useful tool for augmenting human intelligence about a building.
Yes, it's really about augmentation. For instance, when someone gets sick or someone retires and moves on, the data transfer is very imperfect. Compounding that is the fact that the documentation about the system is very imperfect. So let's say an individual has been there for 20 years and they've decided to move on. That person has a tremendous amount of institutional knowledge. And we're not talking about just industry knowledge, but institutional knowledge in the sense of that particular location. It's very difficult, in fact, virtually impossible to have a perfect data transfer when that person moves on. So in many ways, as we build a database behind our inference engine of these relationships, these kind of hidden understanding of the building, we de-risk the situation for the owner. And at the same time, we provide a mechanism for spreading that knowledge throughout the facility team so they become more effective.
Okay, let's switch gears here for a second. I think our listeners would be interested to know what type of data these inference engines is consuming, if you will, and how is this perhaps specific to the buildings industry? Is it, or is this sort of similar across industry when it comes to analyzing data and finding these different relationships?
It's not at all specific to the buildings industry. However, our domain expertise is in the buildings industry, so that's where we're starting with our particular engine. The point is, though, we are using any time series data to feed the engine. So whether it's from a building, a wafer depositing machine, a process manufacturing line, what have you, it can all be pushed into our system, so long as it's time series data. And that's just because we're early days. Over time, we hope to be able to incorporate other types of data, binary data, human processes, and various other things. It's a bit of a stretch when you think of it in the context of where we are today, but at its conception, our inference engine, the Epiphany engine, was never conceived of as a building-specific solution. It is, if you will, a piece of foundational intellectual property for us.
So it sounds like this is a pretty powerful tool from folks all the way from the operations level to the executive team. What types of services can be built upon such foundational tool set?
Well, as I said, we think of it as a foundational piece of intellectual property. The first service that we're deploying on top of the inference engine is what we call OFD, or outcome-based fault detection. And the reason it's different from today's fault detection and diagnostic system is those systems are built on rules. You really have to understand where you are contextually, again, in a building. You have a set of rules or a library of faults, and you begin to modify that library of faults to suit, in essence, the known. You know how things can go wrong, you know how they're related, and therefore you're writing rules to identify issues. That is a completely different paradigm from what we use. What we use instead is the whole notion of relationship. So again, the Epiphany engine is looking at data, contextually unaware of the rules, contextually unaware of how things are put together. All it's looking for at the end of the day is what's changing, how it's changing, and what's changing together. And so it's really focused on the relationship. So our OFD product is a fault detection and diagnosis service, in the sense that we're using our Epiphany engine to identify issues within the system. We're mostly focused on issues that are systemic and they really impact energy consumption overall, the layout, the operational parameters of the system, or comfort. And then what we use is we use our engine to identify these issues, and then we triage them, and then we ticket them, and then we close the loop when they're fixed, and we compare data from the instant it was found to the time period after it was fixed. So it's really a full service, and at its core is this ability to forego the whole set of rules and instead look at how data is really interacting. So through the Epiphany engine and the OFD service, we are identifying hidden relationships, hidden causal processes or assets within the system, and then being able to build a map, if you will, of how those things not only interact, but how you should prioritize the corrective actions that take place.
So it sounds like this kind of knowledge is really powerful for the day-to-day operations of buildings. But it also sounds like having this understanding of the way that equipment functions and then interacts and is interdependent could be really useful for higher level planning purposes as well.
Absolutely. Once you understand how equipment interacts and what other equipment is dependent on those interactions, you can make much more intelligent financial plans and operational plans around the equipment. So for instance, something that appears as a fault, simplistically saying, let's say an oscillation in a particular piece of equipment, yes, that's a fault, and you want to throw an energy impact number and a cost for replacement. But why would you want to do it today is the real question. And that's one of the questions that Epiphany answers, which is basically this particular thing that's oscillating, yes, it's a fault, but it's also driving behavior in 15 other assets that are not showing up as faults. So this one particular fault may have an unanticipated and high influence on other equipment, and therefore you want to replace it faster. By the same token, that piece of equipment could be on the other end of the spectrum, where other equipment that is at fault is driving its behavior. So it may be using a lot more of its life because of faults in other areas of the system. And again, the particular unit is not showing a fault. In other words, it's not doing something radically unusual, but it may be cycling a lot more often than normal. And that cycling is sort of within normal parameters, but it is eating through its mean time between failures. So it cuts both ways. It's driving additional things, and that makes it more important to swap out and plan for. And it may be the tail that's being wagged by a whole bunch of other pieces of equipment, and therefore is going to fail faster. So it's a good tool. It's a great tool, actually, for understanding over time what is really the remaining useful life of an asset and planning accordingly.
And with that, I would like to thank our guest, Steve Nguyen, for joining us today on Building IQ's 10 on the 10th Tech Podcast series. To listen to other episodes and learn more about Building IQ's technology-enabled services, visit buildingiq.com. Thanks for listening, and see you next month on the 10th.